Hello everyone, today we are talking about refraction. So in our last lesson we talked about reflection. So now's a good time to say that when light hits an object, it can do three things. And it can do one of them, it can do all of them. It just depends on what the object is. So it can be transmitted, which basically just says that light will pass through an object. Generally, these are objects that are transparent or translucent. Light can also be reflected. So anytime light is bouncing off an object, that is reflection. And of course, light can also be absorbed. So we have transmitted, reflected, and absorbed. And again, all of these things could be happening at the same time. When we're talking about refraction, we're talking about light that is passing through a medium, so transmitted light. Now, when we're talking about transmission of light, it's also directly related to the topic of the speed of light. So, when light is moving, it does not require a medium. So, a medium could be really any type of particle, water, air, glass, it doesn't matter. Light will travel in a vacuum, so basically space. The speed of light is 3.0 times 10 to the 8 meters per second. This is the speed of light in a vacuum. However, if light is traveling through a different medium, that speed will change. When light travels through different media, it will travel more slowly than the speed of light. So over here we have a few different examples of media. So the speed of light in a vacuum is that original 3.0 times 10 to the 8 meters per second. Water is slower, glass is even more dense, so light is even slower, and diamond is even more dense. Air is considered to be sort of effectively the same as the speed of light in a vacuum. So a vacuum and air, for our purposes, are the same. The thing that is slowing this light down is that the light is forced to interact with the particles of the medium, whereas if we're in a vacuum, there are no particles that are sort of getting in the way. The more dense the particles, the more they get in the way of these photons or light particles. Now, there are some calculations involved with the speed of light. So speed is equal to distance over time, which is represented with this formula. So if our speed is 3.0 times 10 to the 8 meters per second, we could convert it to kilometers just by dividing it by 1,000. So hypothetically, we could calculate the time that it takes for light to travel from Toronto to Vancouver, simply by acknowledging that the speed of light in sort of air is 300,000, and if the distance is 3,400, then we can isolate for t and solve for time. So that was simply the speed at which light photons move in a medium. Now we're going to start talking about refraction. Refraction is the bending of light as it moves from one medium to another. This bend is caused by a change in speed, but it's not a unilateral change in speed, and I'll show you why in a minute. So imagine this. Light is traveling through air and it hits water. Now, water is sort of more dense than air, and therefore its speed will slow down. As a result, this ray will bend. So instead of going directly straight like you might expect, it actually bends. Now, just like our ray diagrams with plane mirrors or curved mirrors, there is still a normal that exists here. So that would be the normal. In this case, we have our incident ray, which is this one right here, and we have our refracted ray. I have gone ahead and drawn our angle of incidence as well as our angle of refraction. Notice that it's still with respect to the normal and not the sort of reflective surface or the boundary. Now earlier I mentioned that light can be absorbed, transmitted, or reflected. So this image is showing you light being transmitted. So it's passing through this water. But it can also be reflected, either partially or fully. So we can have simultaneous reflection and refraction occurring. There's something called the index of refraction. We use the symbol n to represent the index of refraction. Now the index of refraction is basically a ratio of the speed that light moves through a particular medium, so whether it's glass, diamond, air, water, it doesn't matter what, over the speed at which light will move through a vacuum. And remember, that's our 3.0 times 10 to the 8. Because this is a ratio, and both the speed in a medium and the speed in a vacuum should have the same unit, they cancel out, which means our index of refraction does not have any unit. It is simply a ratio. Okay, in this sample problem, we are told that the speed of light in a glass is 1.97 times 10 to the 8 meters per second. As you may recall, the speed of light in a vacuum is 3.0 times 10 to the 8. The question is, what is the index of refraction? So if I set up my formula, it's over here, I know that my speed in the medium is equal to 1.97 times 10 to the 8, and my speed in the vacuum is 3.0 times 10 to the 8. You'll notice that these are the same, so those basically cancel out. And if I divide 1.7 by 3, I get 0.657. So that is my index of refraction for this crown glass. So here's a sample problem. I want you to pause the video and give it a try. Remember, the formula we're using is N is equal to C over V. Pyrex glass is a type of glass that is used in labs a lot. So pause the video, see if you can figure it out, and or keep watching. So I'm going to fill in my blanks. So my N is 1.47, and notice there's no units because, again, it's a ratio. My C is 3.0 times 10 to the 8 meters per second, and I need to rearrange to solve for V. So I'm just going to cross multiply here, so 1 times 3.0 times 10 to the 8 meters per second, don't forget your units, is equal to V times 1.47, and now I need to isolate my V, and I'll do that by dividing both sides by 1.47. So 1.47 will cancel out, leaving me with V is equal to 3.0 times 10 to the 8 meters per second divided by 1.47. If you plug that into your calculator, what you will end up with is 204081632, and that's a bit of a mouthful. So I'm going to roll that decimal place on over. Now hopefully you have learned about scientific notation in grade 9. So if I roll that on over, what I'm left with is 2.0 times 10 to the 8. My units are meters per second, and that is the speed of the light in the Pyrex glass. if you are not sure how I was able to sort of convert this number to this number, I'm going to post a link below that I would like you to take a minute to watch. So like I mentioned, every medium or media will have a different index of refraction. So here's a little table of the index of refraction of sort of the different media that we'll be looking at in class. We have a vacuum with an index of refraction of 1, water of 1.33, Pyrex of 1.49, and you get the point. But the higher the index of refraction, the more that light will slow down as it enters that medium. Or conversely, if it's leaving diamond and entering a vacuum, the more it will speed up. So depending on where it's going, light will speed up or slow down. When it crosses the boundary between two medium, the light will bend, and it is a direct result of this change of speed. So refraction means bending light. Light will change direction at a boundary of two medium. So here's a little analogy. When light, this is our little car, when light enters, goes from pavement to sand. Now, pavement is really easy for cars to drive on. That's why all of our roads are paved. So a car can travel quickly on pavement and slower on sand. If this car enters the sand at a sort of perpendicular angle to the boundary line, then it will continue traveling straight. But if the car enters the sand at any angle or any sort of incident angle, then it will bend. The light will bend if it enters a different medium at an angle that is not 90 degrees. And you will be able to predict which way the light will bend, hopefully using this analogy. So when the car is moving towards that boundary, this, it's the right-hand wheel of the car, or if we're looking at it, the left-hand wheel, tire, wheel, tire, whatever, that will be the tire that hits first. And when this tire hits the sand, it's going to slow down. So immediately it slows down. But this one is still going fast. So if this one is still on pavement, it's still going fast, and this one has already slowed down. What this means is if this tire is going fast, it's going to whip around and force the car to sort of move further towards our normal, if we have a normal right here. So one side of that car going fast causes the car to turn inwards. This is when a car is moving from a sort of a media that is easy for it to move on compared to a media that is harder for it to move in. The same is true for light. So for example, if light is entering, if light is moving from, let's say, air and going into water, there's my little water, then it will similarly bend towards the normal. So the same is also true, except for the opposite, in the opposite situation. So here we have our little, light car entering a vacuum from water. And so what's happening is this wheel hits the vacuum first, which means this wheel is going to speed up while this wheel is still going slowly as it moves forward. And so our refracted ray, let's say this is our incident ray, then our refracted ray is going to move away from the normal. So if it was transmitting through the object with no refraction, we would expect it to go sort of straight through. But because the media changes, we're going to get a refraction of light and it moves outwards. Okay, so the car analogy is one way to predict whether light will move towards the normal or away from the normal. Here's another way. So this is FST, or fast to slow, which basically means if we're moving from a material with a low index of refraction to a high index of refraction, the refracted ray will bend towards the normal. So that's our first car scenario. Our second car scenario is slow to fast, where we have a material with a high index of refraction moving towards a low index of refraction, and the ray will bend away from the normal. And so whether you use the car analogy or whether you use these little fast to slow, slow to fast, you will need to know this. You will need to be able to predict whether the refracted ray will move towards the normal or away from the normal, depending on the situation. Now, there's also something called Snell's law. Snell's law is how we are able to sort of quantitatively determine what that angle of refraction would be. So here in our diagram, we have our incident ray. Here's the boundary between two medium, the normal, and our refracted ray. We can calculate incident rays, refracted rays, or the index of refraction of two medium using this formula. And this is Snell's law. I'm not actually going to get into it too much, but if you want to, go check out the original slides, and there's a few practice problems for you to work on your own. So refraction is also really interesting because it really screws with our eyes. So for example, if there is an object in the water, then light bouncing off the object and into our eyes is refracting on the way. And so the apparent depth of that object is usually a lot shallower than it actually is. So if you're looking at, money in a wishing well, then it seems a lot closer than it actually is. So if you were to reach your arm into the fountain or the wishing well, then you'd have to go down a lot farther than your mind thinks you do. So here's a cute little example. We have, chocolate labs, and when you put them in the water, it changes their big long legs into tiny little dachshund legs. Okay, one final concept to talk about. It's the concept of total internal reflection and the critical angle that it happens at. Total internal reflection, oopsie-daisy, will only happen when light is traveling from slow to fast. So from, for example, water into air. As we change that angle of incidence, there will be a point in time where instead of being refracted, there is total internal reflection, meaning it no longer is refracted out. Instead, we get total internal reflection. So all of the light is reflected instead of being refracted. And this occurs at the critical angle. Well, actually it occurs beyond the critical angle. At the critical angle, the angle of refraction is going to be 90 degrees, which is shown here. So basically it runs parallel along that boundary line. So here is a little image of total internal reflection occurring. This is a lens, so this sort of semicircular shape, and a light is being shone in. it has passed that critical angle and it is being reflected off the boundary. So it's going into the sort of glass object and being reflected out of the glass object instead of coming out the other side. This is total internal reflection. Now, you may have actually experienced this yourself. While at the bottom of the pool, if you look up at a certain angle, you will only be able to see the bottom of the pool. But if you look straight up, you should be able to see straight out of the water. So it's summertime, go test it out on your own if you have access to that. But try and find that angle where all you can see is the bottom of the pool reflected in sort of the top of the water. Well, top of the water from your perspective. One really important use of total internal reflection is fiber optics. Fiber optics are basically a tube where light is being reflected over and over, and it is how we are able to transmit data and information very quickly. So that's it for the lesson on refraction. I'm probably going to post a few interesting links below that would be good for you to take a look at. There's also going to be one simulator below that shows you how both reflection and refraction can occur at the same time, so do pop on that simulator and just check it out for a few minutes. But otherwise, let me know if you have any questions, and good luck!